So here in the second lecture for chapter 19, it's not necessarily this notion of a spontaneous reaction that I want to deal with. Remind you, exothermic reactions, heat released is a good thing for spontaneous reaction. But remember from the first presentation we talked about the endothermic reaction, and if heat is gained, then why does something become spontaneous? And that's where this second lecture comes into play. This notion of what is entropy, putting a finer edge on it, and talk about more than just randomness. Okay. Now in the third presentation, when I start looking at the second law of thermodynamics and the derivation of the Gibbs-Free equation, then I'll actually put an even finer edge in terms of this notion of entropy and what does it all include. Okay, so right now it's just sort of a feel for what's happening in the entropy of the system. For example, I like the solution formation process. I think it's a good illustration of these principles. The diagram above is showing this kind of process. In an aqueous phase, you just have more entropy. There's more ways for the things to move around. There's an increase in translational motion. What do I mean by translational motion? Well, it's simply trajectories, if you will. It's x, y, and the z direction. This solid, there's not a lot of motion in a solid. The ions are vibrating at a certain frequency, and electrons are moving around. That's about it. Once it dissolves and gets up into these solvated hydrated spheres here, the solvent cages, where the water is surrounding the ions, now these ions have, x, y, and z motion, as well as some rotational motion. They can tumble around in the solution. And so there's just more ways for it to move around. Actually, a term that you see sometimes is an increase in the degrees of freedom. Degrees of freedom is just a measure of how many different ways can the thing move. And here, again, rotational to some extent, and then mainly translational motion, or degrees of freedom, is what we're talking about. And that's what's really driving this particular reaction. Now, actually, one point that I want to make here is there's actually a decrease in the entropy for the water molecule. Let's just take a look at that just for a second. Just appreciate the complexity of this issue. Up in this first picture, all the water molecules are pretty much freely moving around. There's hydrogen bonds, really the intermolecular forces that account for water's physical properties. That causes some restriction in the movement, if you will. Once the ions are dissolved and we have these solvent cages, actually the water is more ordered in this particular state, at least to some degree. And so there's a very slight decrease in the entropy for the water. So the overall effect is that this is greater. This increase in entropy for the salt molecule, or these ions, is greater than the decrease in entropy for the water molecule. And so the net result is an increase in entropy. So there are some subtle issues that people deal with for this particular subject that we'll get into a little bit here. But this presentation, I really want to focus in on entropy and see what it tells us. I like this term. Entropy is an absolute value. That's important to note. If we talk about Gibbs-free energy or enthalpy change for a reaction, well, these are relative values. I talked about it in the first presentation. And if we look at one of the last slides in this particular talk, we can actually see what I mean by the relative values. There's the heat of formation and the free energy of formation for different substances, and we don't have to look very far to see what I'm talking about. These are placed as the reference point. We say the elemental form have zero enthalpy formation and free energy of formation. And then when they are chemically modified and you produce some other compound, then there's a change in the heat of formation or the free energy of the formation. It can be positive or negative depending on what you're looking at. Now, the entropy, notice, well, one thing, there's not a delta in front of this. We're not talking about change in entropy. We're talking about the absolute value. Absolute. Oh, sorry. Let me just get rid of that. Absolute value for the entropy. What do we mean by that? Well, I guess first thing to notice that even elemental form has some degree of entropy. There's even in solid aluminum, there is some degree of randomness, if you will, some degree of motion for those particular atoms. And again, like I said, in the case for the sodium chloride up here, there's some vibrational some vibrations that the ions are doing within the crystal lattice, not much. That is a function of temperature. If we imagine here's our crystal lattice at some temperature above absolute Kelvin, the offset from the crosshair here is indicating there's some kind of vibrational motion within the crystal lattice. It's not flying around on the substance or anything, but it's just vibrating in a small region of space in the crystal lattice. That's a function of temperature. That's a measure of entropy for the system. Well, imagine what would happen, and this goes to the third law of thermodynamics. Imagine what would happen if we suck out every bit of energy from the crystal lattice, which, by the way, my understanding is it's impossible to do. There's always going to be some degree of energy in there. But just imagine that we could suck out all the energy from the system, and now everything is stationary on the molecule, which again is impossible to do. There's always going to be electrons moving and protons shaking, if you will, inside the atom. But if we were able to do that, what we do is we reduce the entropy for that solid to zero. There's absolutely no entropy. This is what we mean by the absolute scale for the entropy. Gibbs-free and enthalpy are not this way. Again, we set the elemental form as zero as our reference point, like sea level, and then we measure up and down from there. Well, here, there is one particular theoretical point, 0 Kelvin, at which we get zero entropy, and we can't get a negative entropy for these solids here. And so again, S is an absolute value. And then one other thing that I think is important here is that there's a relationship between entropy and temperature, and we see this in the equations that I use at the very end of this presentation and in the future presentations for this chapter. You see this relationship between entropy and temperature. Essentially, like when you look at, let's look at Appendix C again. Look at the difference in the units here too. We have a certain amount of heat per mole or per amount of the solid for both the enthalpy and the Gibbs free change. Entropy is different. Yes, there's a certain amount of heat associated, energy associated per mole, but there's also that Kelvin term that's thrown into the mix. What is that telling us? Well, again, it's implying there's a relationship between entropy and temperature, but essentially what we're doing is that, what amount of heat have we added to the sample per the temperature change that we're talking about, and that's related to this notion of entropy change. Okay, so there's a relationship here, and even if you go back to the early 1800s and scientists studying really steam engines and the efficiencies of steam engines, you see this issue popping up, and they didn't have the terminology or the technology we have now, but they certainly appreciated this issue of heat transfer over a particular temperature range in terms of the efficiency of a steam engine. And that has, over the course of 2 centuries, developed into a very mature science that we have here, and this notion of entropy. Now getting into the details of the origin of entropy is is beyond the scope of the course, and actually it's a rather involved explanation. So of course we're not going to go there. Just appreciate the fact that there is a link between the entropy and the temperature at which the sample is at, or the temperature at which that heat has been transferred. Okay, and again, we see that in some of the calculations coming up. Now, before we do the calculations, let's just conceptually walk through this notion of entropy. And the two that I want to focus in on here are the two values for water. They don't have solid water down here, which is fine. This certainly tells a story that we need to look at. The graph tells a story. Notice, remember, if I talk about entropy associated with degrees of freedom, you know, how many different ways can the thing move around? And we'll even put a finer edge on degrees of freedom. We'll cover what that means here in a few minutes. Well, a solid, you know, we have a crystal lattice, it's stuck. It's not going to really move all that much, that solid. Whereas if you add enough heat, you know, over a particular temperature range, then the gas molecules can easily move about the flask. There's just a higher degree of freedom. There's just more ways that molecule can move around, and that's typically shown with the entropy for, if you look at the standard molar entropies for different substances, you see that particular trend. Now, it's not always true. You see that, you know, this particular solid has a greater degree of entropy than that particular liquid, so you can't, I mean, that's like comparing apples and oranges, ferric chloride to water. But again, the general trend is true. As you go to the gas phase, you tend to see an increase in entropy. So the biggie here is that relationship. Gas is an increase in entropy. And we can actually use that in this kind of process, just predicting the entropy change. Now this is a qualitative analysis. Remember, qualitative is just like yes or no, up and down. You know, you're giving some kind of descriptive term. Quantitative is numerical. That's the last two problems for the talk. Well, in example A, we have a solid going to gas, and we have the same compound. So that's real simple. We can easily say, well, you know, just by eyeballing these numerical values, we see that typically these are larger. We see a graph plotting the entropy versus temperature here with the different phases, and we see that's clearly an increase of entropy. And I think conceptually we can imagine that as well. Again, the solid doesn't move. The gas molecules can translate, rotate, vibrate, all kinds of different degrees of freedom. And so one would say, well, that must be obviously an increase in entropy. And if we quantitated this, we would find that to be the case. And we'll quantitate one here in a few minutes. The second one, well, you got solid on both sides, and then this is the only place where gas is showing up. And I guess I can include part C as well. You got two gas molecules over here, and then you have a solid over here. In both cases, that phase change going to the solid is actually decreasing the entropy of the sample, just based on the phase change. And this is really the easiest one to identify in terms of predicting entropy change. And note, it doesn't matter, if you're talking about this gas to solid transition, it doesn't really matter that we have, I guess in some cases it'll matter. I can't think of one off the top of my head, but you know, I never like to say never, you know, in science. It's just, I don't typically do that. But, you know, you can essentially always look at the gas and the solid phase to predict the entropy here, irregardless of whether the chemical is being modified or not. Okay. Now this last example takes a little bit more thought. You know, think about what we're looking at. We're all talking about gas phase, so that, you know, the phase transition does not help us here. What helps us here is recognizing the fact that we have 3 moles of G of gas here, and then only 2 moles of gas here. You know, all the gas phase molecules that we talk about in this textbook, practically, Gen Chem 1 and 2, we treat them as ideal gases. So it doesn't really, their identity is going to matter in terms of the chemical process that occurs, you know, in the reaction. But in terms of just like PV equals nRT, or this entropy sort of qualitative description, it doesn't really matter what you're actually looking at, the chemical compound. The fact is, we are reducing, the number of gas molecules are actually being reduced from one side to the next, and that is an indication that the entropy is reducing for this process. So you don't have to have a bona fide phase change to have a reduction or an increase in the entropy for this kind of a process. You can just count the number of moles of gas that you have in front of you. Now again, we're not quantitating the entropy change. If we wanted to quantitate the entropy change, let me just go ahead and jump forward and show you how we would do that. We have the reactants on this side, we have the products on this side, and there are a set of equations, and we can talk about enthalpy, Gibbs free energy, or the entropy change for a given reaction, and each one has the same form really. You're just changing, changing the I see a typo. I'll talk about it in a minute. But you're just changing the parameter that you're measuring. The typo is actually the F. We don't talk about the entropy change of formation. All we talk about is the entropy for that substance, because it just is. It goes back to this idea of it being an absolute scale, whereas these are not absolute scales. Long story short. But in both cases, you got products minus reactants for these equations. And where do we find these values? Well, I guess, the N and the M's are the number of moles, and that's simply acquired by looking at the 2 and the 1 and the 2 for a given equation, and you would substitute them into the formula. The other parameters, the delta H, delta G, and the S, well, that's simply acquired by the Appendix C here. And again, we will use these equations down here for bromine on that very last problem that we're going to do in just a few minutes. What is it? This is a plug and chug game when you use these equations. Now, for a rather long equation, it can be a lot of numbers being thrown at you, but if you keep your wits about you, again, it's just plug and chug. It's no more than that. We're using these thermodynamic parameters here, the tabulated form, to predict outcomes for a reaction where we don't have to go into the lab and measure the quantity. Because honestly, especially here at AB Tech, we don't have the technology to do that. And in other cases, I'm not a thermodynamicist, but some of the parameters, some of the measurements may be rather tricky. And so that's one of the powers of thermodynamics, is that you can use these theoretical constructs to actually predict outcomes for a reaction. And we'll see at least one example of that actually in this presentation. Another thing that can affect entropy is just the volume change. Now honestly, this is a minor issue, but it's something that you should be aware of, and you should be able to think through the process, tell you the truth. I mean, let's say we have 100 molecules of a gas in flask B. The stopcock is closed in the first picture. Well, if we allow the gas to move about, what's it going to do? It's not going to stay in flask B once the stopcock is open. It's a spontaneous change, happens very easily. It's irreversible. There's no way to back out these molecules along the same path as we did before. Okay? Reversible processes are theoretical constructs of chemists more than anything else. All the chemical reactions that occur in nature are irreversible. Now they may be spontaneous or non-spontaneous, but that's a different matter. That's right from the first lecture. That's a really important equation. It's very simple, amazingly simple once you use it a little bit, and it's a very powerful equation in terms of predicting spontaneity. Anyway, third presentation, the next one after this, it's only about 25 minutes long or so, and what it does is it ties in the second law of thermodynamics with this particular equation. It shows a derivation of this equation, and it puts a sort of the why into everything. Why are we using this? Where does it come from? all the sort of meaty questions that I didn't want to deal with in the first and second presentation is dumped into the third presentation. So the third is important in terms of conceptual connections, some of the things we're talking about here. I digress. Well, obviously, I mean, 50 and 50, they're going to spread out essentially equal numbers on either side. That's just part of nature. Nature abhors a vacuum. I can't remember who said that. I don't know, Pascal, Bacon, who knows. But that's what's happening. You have a vacuum here. It's just a natural tendency for things to fill a vacuum. And what a chemist would say is that there's an increase in the number of microstates. You know, how many different ways can we arrange those 100 molecules? Well, there's a certain number here that I guess would be rather large, you know, in terms of what are all the different possible positions that those molecules can take in. Well, if you double the volume change, then as a result you see this increase in microstates. There's an even greater number of arrangements of the 100 molecules when you're dealing with a larger volume of space for them to travel in. And so that can direct chemical or direct processes in nature. I'll put it that way, and it can affect the entropy. More importantly, molecular formula, and it's getting into this issue of degrees of freedom. Remember, you know, I talked about X, Y, and Z. You know, throw a pin across the room. What do you see? You see a trajectory. It's traveling in three-dimensional space. Molecules do the same thing. They do it a little differently, but that's what they do. So we'd say there's 3 degrees of freedom here. You know, we're counting up how many different degrees of freedom can a molecule have. And physical chemists talk about this a lot, or at least you see it in the class a lot in certain places. So for us, all we're worried about is, you know, what are all the possible molecular motions? Vibrational and rotational are playing a role here in terms of contributing to the entropy of the system. If you jack up the degrees of freedom, then you've increased the entropy of that particular molecule or that particular system. Now, where the vibrational part really comes into play is it was a series of molecules such as these hydrocarbons. It's where we really see it. You know, all of these are gas phase at standard temperature and pressure, which I'm going to talk more about standard temperature and pressure, and I'm going to talk more about the delta, or the naught, I should say, that you see in those parameters. It means these measurements are taken at standard temperature and pressure, which honestly, I mean, few reactions actually occur at standard temperature and pressure. It's sort of an idealized state just so we can get something on the page, to tell you the truth. And then in the very last lecture for this chapter, what we do is, well, what happens if this comes out of standard temperature and pressure, standard conditions? Anyway, let's stick with standard conditions now. All of them are gas phase at standard conditions. What's happening is that the molecular complexity is increasing. So complexity is increasing as you increase in molecular weight, is essentially what you're saying. And so as you start adding more atoms and more of these bonds, well, they can just move more, not just in the XYZ direction, but there's actually these vibrational states within a molecule. When infrared radiation, which is just light energy that's felt as heat on your flesh, that's a simple definition of it, when infrared radiation strikes a molecule at a certain frequency, what it's going to cause are these different vibrational states. You know, molecules often are talked about in the context that, you know, we write them, we almost talk about them as sort of static entities, if you will, but that's not reality. You know, in reality, these bonds, well, one thing, there's a slight, just a vibration anyway here, but in the nuclei, let's say, electrons moving around, it's a very dynamic system. Electron density can be shifted based on electronegativity, and then in this particular context, you know, you can model the bonds as little springs. And so, you know, if you pull a spring apart, you know, if you have a point here and then you got a spring and another point, you know, there's a certain state where it's relaxed. And then if you grab that point and you pull it, and you stretch it out, there's a restoring force. You know, it's wanting to go back in the relaxed state. And if you let it go, it'll wobble. It'll vibrate, if you will. Well, here you see the different vibrational states for the water molecule. This is a symmetrical vibrational state where both bonds are being stretched out at the same time. This is a bending motion where the bond angle is changing. And then this is an asymmetrical stretch. One's getting long and one's, well, getting short is what we have it. We call it an asymmetrical stretch for water. The number of vibrational states, again, increases with complexity. And so as a result, that's why you see the numerical value for entropy increasing as you go to the higher molecular weight hydrocarbon here. And that's the general trend that you see for all molecules, essentially. And so complexity of the molecule can assist us in terms of predicting entropy change. And again, in terms of a qualitative sense, we're not going to get into a quantitative measure of entropy just looking at that molecule. Our quantitative measure, well, it's sort of where we're starting it now to some degree. So the next few slides, there's a couple problems here, and then a couple concepts that I want to deal with. And ultimately, I mean, I keep going back to this. It's a really important. All these equations are important, along with Appendix C. Oh, by the way, of course, you will be given Appendix C. You'll be given this data on the test. You can use it for the quizzes, etc. I don't ever have people memorize this data. But these equations are really important for these types of calculations. So, you know, I've already talked about phase change, and this would be liquid water. This is solid water, ice. And of course, there's increased entropy over here on the liquid state. I've already talked about that. There's a notion of temperature dependency for a spontaneous change or not. And what I mean by that is we know that water melts at 0 degrees Celsius, or begins to melt anyway. And you know, at some point in this melting process, you know, if it's slow enough, which actually, you know, this notion of a slow infinitesimal change of the system is in reference to a reversible process. Okay, so phase change is describing here is probably about as close to a reversible process as we care to get. Okay, you know, if you jack up the temperature anything above 0, 1, 2 degrees Celsius, then it's an irreversible change, and it's a spontaneous change, you know, greater than T. And so there is an issue about, you know, at what temperature does the system change from being a spontaneous process to a non-spontaneous process, and that becomes important. And actually, it goes back to this particular equation, the Gibbs-Free equation, which again I derive in the third presentation. Well, at this particular process, well, we're going to describe this as an equilibrium. You know, we're at a constant temperature. There's a certain amount of ice, and there's some liquid here, and in the sort of the what I'm setting up here. Delta G is 0 at an equilibrium process. If you plug that into the equation here, what you get is this new one, and I want to solve for delta S, and what I see is that delta H divided by the T at which the process occurs is equal to the entropy. Now remember what I said. I said back here, third law of thermodynamics, that there's this relationship between of entropy and temperature. You increase the temperature, you start getting molecular motion, an increase of entropy. And that's a function of how much heat has been transferred in the system versus T. So I showed the equation over here in a sort of in a simple form, and then here sort of deriving it on this page. Now, the book actually gives you this particular example. And again, to go into the details of this reversible process any more than what we've done, and then I'll talk a little bit more about it in class, but this is really an idealized state for a chemist, to some starting point to get something on the paper, if you will. Not quite, but it's more complicated than that. But what it does is it gives us an equation. It gives us a way to measure that entropy change is associated with the heat for a particular temperature. What units are we going to have? We're going to have joules over Kelvin. And if there's 1 mole of the substance, that's joules per Kelvin per mole, which is the same derived unit that we see on Appendix C. For all entropy change, you see this particular unit. And it goes, again, I'm sort of coming at it a different way, but I'm trying to use an example that an equation that we've already talked about and used in the first presentation to get at the equation in the book. It's from a different angle, okay? And one other thing we can do, if we solve for T here, then we would establish, that temperature at which the spontaneous process stops. Well, I guess I should say where the spontaneous process becomes a non-spontaneous process, or vice versa. And the fourth presentation is where we'll get into this equation, or the use of the equation in that context. Right now, what I want to do is a couple of different calculations. We have ethanol. We have the molecular weight for it, and we have the boiling point there. So this is going to be the temperature at which the process occurs, is what we're getting at. And while I'm pointing to this thing, I'm just going to go ahead and convert it to Kelvin. Essentially, you always convert temperature to Kelvin. So just automatically do that for this chapter, for any of the chapters in this course. That's a normal boiling point, so that's a transition. Oh, we know what that means. I'm going to abbreviate it. That means that we're going from liquid to a gas. That's the boiling point, so that's a liquid there. E2OH is my abbreviation for ethanol. Not just mine, but a lot of people's abbreviation. Molar enthalpy of vaporization. What would that look like? Well, if I wanted to give that a symbol, I would give it enthalpy of vaporization, and it's 38.56 kilojoules per mole of the sample. Do I have 1 mole of the sample? Well, I don't know yet because it's given in grams, so that's going to vary here. But if we had 1 mole of ethanol, then that numerical value there tells us the heat of vaporization for ethanol for just 1 mole of it. So vaporization, that's what we're describing here, liquid to gas. What is the problem asking for? It's actually asking for the entropy change when the liquid condenses. And so let me switch pen colors here because we're jumping concepts now. That's condensation, going from a gas to a liquid. We have the numerical value for vaporization. Well, it's not too far of a stretch. It's the same amount of heat, it's just going in a different direction. It would be minus 38.56 kilojoules per mole. That's what it's talking about. Condensation, actually vaporization is easier to think about because we boil water. If you cook even a little bit, you're going to boil some water. You have to put energy into the water to get the phase change to occur. And that's what's describing here. This is an endothermic process. It's a positive value here. The reverse process, it's the same amount of heat, but that amount of heat is being released when it condenses. Released heat. It's an exothermic process. This is the value of Q that we're going to use for our calculation. Because remember, we want to know the change of entropy. We established that equation earlier. Delta S is just the amount of heat that's been transferred during the reaction, during the process at a given temperature. Now, at the phase change, the temperature stays constant, so it's an easy numerical value just to plug in there. So we actually have 351.5 Kelvin. There is a difference between heat here and then the enthalpy change there. The enthalpy change is describing that of for 1 mole. Well, we don't know if we have 1 mole. Let's see how many moles we actually have. The molar mass for ethanol. And honestly, you should be able to do this without too much fuss. This should look very familiar to you at this point. If you divide by the molar mass, then it tells us that we have 1.38 moles of ethanol in our sample. And so we want to know the amount of, we need to know the entropy change for that amount of the 1.38 moles of ethanol, but we don't even know the heat change yet. All we know is that there's a net release of 38.56 kilojoules per mole of the sample. We have 1.38 moles of the sample. Well, dimensional analysis tells us if we multiply the two, then we increase the amount of heat that's actually released for the sample that we're considering in this problem. I'm going to go ahead and change it to joules. So there is an additional factor here, right? There are 1,000 joules and 1 kilojoule, so we can cancel that out. Okay, so I'm going to convert it to joules. And another thing I'm doing, textbooks, I don't care which one. I've never seen a textbook that's good at significant figures. They talk the talk, but when you get to a problem, sometimes it just goes haywire. I'm going to use, I know the significant figure rules pretty well, and so I'm going to use them to the best of my ability. Looking at this problem, I got 3 sig figs here, I got 4 there. Conversion factors don't matter. 3 sig figs have to win out in a multiplication or division problem in this context. So I'm keeping 3 sig figs here in joule. Now I have the value of the heat that's being transferred in this particular phase change that we're talking about, the condensation. There's this amount of heat is being released, negative sign, at a particular temperature. That's that relationship between heat change at a temperature that tells us the entropy change for this particular process. And it comes in at 151 joules per Kelvin. Now I will tell you the book, 163 joules per Kelvin. I'm not sure where that number's coming from. I looked over my work. I don't see anything obvious. I'm recording this for posterity, but I can't see my mistake. So if you see my mistake, give me an email. I'd appreciate it. It's amazing, when I'm in the thick of these problems, the little things that I miss. But anyway, I can't see where my error is. If I look at it again, I'll send you an email if I figure it out. But anyway, order of magnitude is the same. It's within 10, 12 joules per Kelvin. It doesn't. It's close enough in my book anyway. And as far as I can tell, I've done the calculation correctly. So here's one example of how to calculate the entropy for a phase change here. And in the third presentation, I come back to this, and I'll link it back to the second law of thermodynamics. Just let me comment about second law of thermodynamics for a minute. In my book, it's one of the most interesting and most important laws of science, practically. There's so many variations of it, and maybe I'm doing you a disservice and not talking about it yet. But again, one thing I'm trying to emphasize on this thermochemistry, which can be complicated enough, I know. I want to emphasize, those equations and those concepts that are really get you through the meat of the problems, the bulk of the problems you got to deal with. I've introduced the concepts, I've introduced some of the calculations, and then in the third presentation, what I do is I back up a little bit and say, well, here's the second law, and here's how you use that to derive Gibbs free energy. And then I try to package that into the concept of what does it take to be a spontaneous reaction. Okay, so the third presentation is pretty meaty, pretty rich in terms of content. Not really a lot of calculations. I do use this equation, but not a lot of calculations. Mainly concepts. Last one here, prediction of physical properties. And now here we're going in a different direction. Here we use the boiling point and the enthalpy vaporization to calculate the entropy change. And on here, what we're going to do is actually predict the boiling point. Let me go back to blue. I like blue better. What is this process? If we're boiling something, what does that mean? That means we're going from a liquid to a gas. I know it seems very simple, but what I'm establishing is that what's on the reactant side and what's on the product side. Okay, and then again, if this is at a phase change, remember, please, phase change, delta G is equal to 0. That means that this expression becomes, well, the Gibbs-free equation becomes this expression. T is that temperature. T, if we solve for T now, what we have is delta H over delta S. No, look at that. As soon as I said it, I wrote it backward. Isn't that funny? Delta H over delta S. This is of the reaction. Okay, it's too small. I would put quotation mark because this is not a reaction, it's a phase change. Okay, but it's essentially the same. You can use this in a reaction. Actually, this equation of reaction would tell you at which temperature that system goes from a spontaneous process to a non-spontaneous process, which I think that's the third or fourth time I've referenced that. Last video talks about that. Very important concept. Here all we're doing is we're using that to predict the boiling point for this particular phase change. Well, we need delta H and we need delta S. And we're not... let's see. So we're going boiling. We're going from a liquid. There's your reactant, and then to a gas. There's your product. I mean, we just can't take the numbers as is off the chart. We have to. We're treating this as a chemical change. Well, it's not. It's a phase change. We're treating it like a chemical reaction where we have products over reactants. So these equations can be used in any context, really. If you have something going to whatever, whether it's a phase change or a chemical change, you can use these equations to predict, in this case, delta S and delta H. Let me set it up for delta H. It's going to be the same way as for delta S. It's just that you're going to be using different numerical values. So again, it's products minus reactant. So the first column is the heat of formation, the enthalpy formation, enthalpy formation for bromine in the gas state. Let's set that up. So we're talking about enthalpy change for the process, reaction, is going to be equal to, well, the summation, I'll put that in brackets, of there's 1 mole of this product, if you will. It's heat of, or enthalpy of formation, what did I say, 30.71 kilojoules per mole. And that's it for the first part. So this portion is simply this section right here of the products. Again, like I said, N and M, they are the number of moles for whatever compound you're looking at. These two are relative terms. We can use that. Or relative values. That means that their standard reference point is the elemental form at STP. And so standard temperature pressure, bromine, the simplest form is going to be found as a liquid, diatomic molecule as a liquid. Scientists say, okay, make that 0. All the other changes are compared to that. And so all these other values you see at top and bottom are compared to this as being the standard. Excellent example to begin with, because what's 1 mole times 0? Right, that just goes to 0. So actually this standard state for bromine, at least for the enthalpy change, well, it drops out of the expression, essentially, is what I'm trying to say. So I have 30.71 kilojoules is the heat of, well, liquid to gas. That would be the heat of vaporization for this particular example, this particular phase change that you're looking at. Oh, kilojoules per reaction as written. It's a phrase I use occasionally, and I'm not the only chemist that use this equation. Per reaction as written. You know, if you have a more complicated reaction and you calculate, you know, delta H of that reaction, and it gives some, I don't know, 500 kilojoules. Let's say, I don't know, for that one. All that's saying is that there's 500 kilojoules change per reaction is written, per 2 moles of that, per 1 mole of that, and the formation of 2 moles of that. And so oftentimes you do see that mole unit being dropped in these types of calculations. And you hear that phrase, per reaction is written. You know, the situation for the entropy change is a little different. There's look, there is no zero. To have zero, you got to have 0 Kelvin, which really you can't get there. I think the best they can get is something like 10 to the minus 7, 10 to the minus 9 Kelvin. I mean, that's cold. Don't get me wrong, that's extremely cold, but it's not zero. There's still some heat there. Okay, there's still some energy associated with that system. So we can't get really. That's more of a theoretical concept. I don't think experimentally. I don't see how it can be reached. Anyway, that's where you would get 0 entropy, and that's so anytime you do the entropy, anytime you use the entropy equation here, you're going to wind up with numerical values on both sides. I guess is what I'm trying to say. And let me just set this up without talking it to death. Moles Kelvin. You know, there are more units or more units for entropy. The products. This would be the entropy for the vapor state of bromine. 1 mole. Again, 1 mole is just taken from the reaction as written, the molar coefficients. And then it's a solid on the reactant side, so we would expect, and we do see it, we do see a decrease in the value for entropy. And if we plug those values in on the calculator, we get 93.0 joules per Kelvin as per reaction as written. Now, you know, now I've measured the enthalpy change and the entropy change for the phase change for the process that I'm looking at. Now I can talk about the temperature at which that occurs. And you know, the temperature at which it's at equilibrium, really. That's the definition of the phase change, if you will. I do have to watch out for my units here. So what I did is I just changed kilojoules to joules, moved the decimal 3 places, and then 93.0 joules per Kelvin. And then we do get, let's see, 330 Kelvin is the boiling point for the element. And on I can't remember what page number it is. This table 11.3, the book is telling us the experimental value is 332 Kelvin, which is in agreement. So again, you know, we don't have to go in and, you know, calculate the or measure, experimentally measure the boiling point. We can calculate it. Again, that's one of the powers of thermodynamics, if you will. It allows you to calculate things without, you know, actually experimentally having to go through that process. Okay, so again, the next lecture is conceptual. It's short. It's a very important conceptual process. That's second law of thermodynamics and the derivation of Gibbs free energy. And then the last presentation is dealing with some more calculations. Actually, we're going to link this particular chapter back to chapter 15, the equilibrium constant. And so that's what we have to look forward to. Okay? Thanks.